But this process measured, most people don't even know this process. I didn't know about this process before reading this paper. This process came and cut everything out. In what sense? We can forget that. That's for experts. 400 MeV, 0.4 GeV. So this gauge over minus L tau, because of this cross-section measurement data, this Z prime from this paper, which they passed review at least to this extent, this L minus L tau gauge boson has to be extremely light, lighter than the K-on, and that ticked me off. Okay? But anyway, I was fascinated saying, it's quite orthogonal to my usual thinking, or most people's thinking. New physics is at the high scale. Here, from data, it implies this relatively well hidden new gauge force can sustain a very light gauge boson. It's mind-boggling. So I went on with this. Okay, so this partially answers, well, that doesn't answer your question. The reason this thing survives is because it becomes very weakly coupled, okay? And this experimental sensitivity runs out. It's weakly coupled because it's about 1,000 times weaker than electric charge. So it's like a so-called milli-charge coupling, okay? So this is, we quickly learned that there's this other direction. So if you want to explain G minus 2, you have this very light object. If you want to explain P5 prime, you have a generic, 100, 1,000 GeV scale Z prime. So we had two projects in one paper. So we went on to study. So as we were studying, shortly after, I said, well, this is their model. I didn't go into the model building. I didn't even give you the Lagrangian. So I gave my senior advice. You see, it's very shortly after the meeting, probably over a beer. I said, well, look, you can go on and do model building, but there are too many parameters. So given that down quarks, bottoms and strange, gives the strongest constraints, I advise just to throw them away, and it's doable. So let me teach you, this is something generic, Occam's razor. You can spend your life in details and never get out. So Occam's razor is not fully easy to explain. Basically, if I use it with vulgarity, cut the crap and get to the point, okay? Because quite oftentimes you're not doing crap, you're doing beautiful calculation, you're doing beautiful instrumentation, but it doesn't lead anywhere. You have to somehow set a box and say, I do things within this box, and that's roughly the Occam's razor, okay? So they followed my advice, cut the crap, because I said this is too difficult. So we just say we imply a Z2 symmetry to kill the coupling like this. It's doable, and we don't care. After all, my motivation was this guy. But even with this guy, quantum physics tells you that this diagram is created. So the core is the same as this. But I can loop around with a W and can change this external standard model part into down-type products. So this standard model of scissors loop became what we needed to compute, okay? And as I said, the paper was finished in the middle of December. So this is what I meant in the abstract. You do regular research. Your boss or you yourself find a topic, okay? And then you would need to work it out, computation or data analysis or instrumentation. But here, because we have the S, because in principle, this Z prime can be accessed even from K-on decay. But for a long time, for all the time, our goal was to study top decay. So these were providing constraints, okay? K-on to pi-on transitions, B-meson to K-on transitions, if you remember, or halfway to remember this quark content. So these are just the details, not even the full details. So here we come to the K-on frontier. Oh, you thought it was not the frontier, you thought it was backyard, okay? For this oldest frontier, what remains for new physics is really For these two modes in the title, this Grossman-Nir bound is as follows. It states that the K-long decay cannot exceed about 4 times the K plus decay in the same framework. It's pretty sound because it's based on isospin and the K plus K0, K plus K long lifetime ratio. Very straightforward, hard to violate. And look, 10 to the minus 9. We saw a measurement in B physics of order 10 to the minus 9. So kaon guys have been facing this all the time because they have been around for much longer. So having stated this, these are still frontiers because there are 2 ongoing experiments trying to catch glory. And the theme of the talk, the good result that came out is that we point out some possible Koto surprise and more. Maybe I will have to skip the more. You are the time control. So here I say there's this NA62, but there's a predecessor experiment done at Brookhaven. So these are old plots, 2009. So I'll just tell you what it means. There are stringent bounds to 10 to the minus 10. Whatever that means, it's very stringent. But there's a window here. So we understood why there's a window. I'll come back to this. But again, a few days later, I said, well, there are loose ends. We don't fully understand this. And in particular, I should go and chat with Bob. Remember the Bob Sheng Lao Da? Because he's on Koto. I said, what is the situation for K-long decay? By the way, I forgot to put down one slide. I wrote this as an email or minutes to the 2 young friends, and I said, well, over beer, I said, well, whatever K-long does, it's going to be worse or poorer compared to K plus, because K plus has more control. That was the backdrop and mindset. But then I did the homework, and what am I trying to do here? So and of course, helped by discussion with Bob, I understood that there's a kinematic control. They just don't look at this part, okay? So if there's a Z prime going through, they just don't see it. So the previous chimney or the bound was by a different kind of a measurement. So the predecessor experiment compared to the new experiment, the methodology deviates a little bit, but the kinematic control, these 2 windows, is about the same. So the reason is this, there are too many events here. So they choose not even to look at it. So kinematically, they select events only contained here. Any events here is sort of the control, but they don't look at it. So this is what I mean that I check at the Pi0 bound paper, I'll mention that, compare the NA62. So the outcome is as follows. So this Z prime that we had in mind, if it goes in for this type of, for the K plus experiment, where's K plus? They don't even look at it. And the reason they have this bound is because they make a measurement separately of the probability that the Pi0 decays in a new bar and combine the limit. But if you look at this limit, then this is what things people don't fully notice. If you combine this limit, this statement, if there's an object which is of the Pi0 mass, which means this window, it's a much weaker bound. Whereas here, it's a much more stringent bound. But people remember only the much more stringent bound. So this is how, in those days, first talking with Bob, then talking with the theorists, we uncovered saying that there's the kinematic control does not exist for the K-long experiment. It's a nothing-to-nothing experiment. In what sense? K-long they cannot see. So it comes in, but you don't see it. There's 2 photons. They collected 2 photons, but they cannot ID it as a Pi0. They don't know the momentum. So that's why they call it a nothing-to-nothing experiment. So given the predicament, what they do is to veto everything. It's a lot of hard work. But you cannot veto something that you cannot see. Okay? So that's how we uncovered that it may happen if an object goes through the pi 0 window, then the K-line experiment, because the totally different mindset, they can feel it. Here they turn a blind eye. Here they're just blind. So the sensors are different. So this is where you see that So we find a surprise. The blind man is blessed by his senses, not by his eyesight, and thereby the Grossman-Nir bound can be evaded. We did not evade the Grossman-Nir bound. I will not go back. We have a poorer limit from a direct search from this experiment, okay? But the perceived bound that even the K-line experimentalists have been using are violated. This is the red crossed out, whereas we do not violate the concept, okay? So this was trivial, but that's the serendipity thing, okay? Remember I said I went to Bob to discuss, carrying the mindset saying, whatever K-long does, it will be worse than K plus, because K plus to pi plus has more control. But here I've laid out to you that there is a hidden blessing. There's a second spot. Okay, so then, sorry. When I get agitated, I copy them. So let me give you the mind's, eyesight or mind from Koto. That's their logo. Grossman-Nir limit. This is the unit. 10 to the minus 11 is the unit. So this is from their proposal stage. Okay, much poorer figures. And you see that this red point is coming from, so this is the bound coming from the E949 experiment. So this is the limit set by the Grossman-Nir bound. So this is their business space. They think this is the physical space for them to probe. But what we said, if this thing happens, let me lay it out with you. Okay, actually with that backdrop, last year, Koto claimed to reach their predecessor experiment sensitivity. But it looks very poor because it's way up here on this plot, okay? But what we pointed out then is that if something happens that this X0 particle has a pi 0-like mass and this experiment simply cannot feel it, then this whole region is zone. This is a Greek spelling. This is pronounced zone, right? As a la xenophobia, whatever.
I think you mean the Z.
Huh? No. What I mean is that this is much more general.
Yeah.
We started with a Z prime, but the observation is any X0 that escapes the K plus experiment, the K-long experiment can capture by being blind, okay? So we open up this discovery space for them, and this one as well, I think. No, actually only up here. Okay, so this is the main point of the paper. So this I just put it out a little bit bigger, and to explain the title. So we violate the Grossman-Nir bound, the numerical one that people, even Koto experiment has been adhering to all the time. But we do not violate the Grossman-Nir concept, okay? The K plus to the pi plus X0 does happen. They just simply cannot catch it if it's a pi 0 type mass, okay? So this is a very simple point, and I think that's the main point that got us into this letter. It need not be the leptonic force. It does not even have to decay, so long it gets emitted from the Ki, okay? So it's a very general statement, but for our model, let me spend a few minutes on these implications. This is the usual bland statement, phonological results. This is the more astounding. Bonanza in our times, maybe many discoveries, but I guess I should zip through this now. This part is now for the experts. Let me not explain this, but notice that this different experiment at Stanford finds a very similar thing in B2K transitions, a sister effect that can be interpreted in the same way. Bell has not really achieved this. Let me not explain this. Still trying to end in time. But the Babar result, if you say this is data, it nicely illustrates this fictitious Grossman-Nir bound, because the Babar result covers from the current series bound all the way down to the Grossman-Nir bound, and if we just have more data, sorry. I've advised Pauci, etc., saying that Bell needs to really follow this analysis and also go on with the Bell analysis, the Bell 2 analysis. View this as discovery zone. Okay. There's a second window outside of the pi zero mass. I didn't explain why there's a such window, but a predecessor experiment of Na62, Na48 made this kind of a Hou measurement. What we played around here is that there's a nominal excess. Don't take it seriously, but I told my young friends, this is like the most serious excess one can get, and it suits our purpose. Take this range of excess, do the mathematics, and we get this ratio, excluded, okay? That the effect has to be inside. This is the previous Babar we saw. And LHCb, if the Z prime has this mass, remember it couples to muon number. So with this mass, the muon mass is 105.6 MeV. So this Z prime can decay to mu plus B minus. But if you look at the binning here, people at LHCb, a fancy experiment, do not think about a very light particle to be discovered. So they don't do the binning, but I think this is potentially diluted, but there's a mild excess here. So if I take that excess, it's all happening in our bin, we get this bound. But because of the dilution, I think this is better done by experiment. There's juicy stuff I can tell you about LHCb communication, but let's skip that. So they have this higher luminosity result, again, excess. But now, they do not go to the target zone we have, so they exclude. If there's this point, it depends on the detector resolution. They may not even be looking at it properly. There may be this object there, and the current experimentalists are just not prepared for it. Okay, they can do it. Okay, come back to our original target, and this was for John. It gets pessimistic. Because of these bounds, it looks like 10 to the minus 7 is hard to reach, okay? Okay, so I'll leave that as that. Okay, this is astounding, but I'll just tell you the signature. We have this exotic scalar that generates the Z prime mass. So you have this process that decays to Z prime. It can be produced, and then we have a pair of dimuons that's very low in mass. Now this is real data. What this plot says is that by going to the so-called sideband, the analysis says one expects 4 events here. No events here. Not explained, but it can happen. And the only event that pops up is the event of this kind. Now this is way, way, way too early to tell, but it would be astounding if discoveries are made this way. So that's what I meant that there's this bonanza. So Santos, this is the answer to your question. You can see that if the Z prime is heavy, of course there's no lifetime issue. Even as light as 200-300 MeV, the lifetime is sub femtoseconds. So even in this plot, I think the lifetime is, it doesn't really give you a decay length, okay? Okay, so let me conclude now. Oops, oh gosh. I hope I have not overemphasized serendipity, finding valuable and pleasant things that are not looked for. We didn't set out to say I want to find a loophole in the Grossman-Nir bound. I myself, everybody has taken Grossman-Nir bound as solid. Proposals were written and granted, okay? So we didn't set out to do that, but the serendipity thing happened. We walked the walk, walk the walk, working hard. You know, as I said, I was motivated because a friend sent a student, and I better look after her well. I'm looking after a group, finding topics to do, and then some serendipity happened. So this is not quite a conclusion because I'm not going to come here and summarize all I said. Okay. Now, are there any Koto people here? No. Too bad. Bob himself is also not here. This is the joke for Koto. Got it? Well, if you're too young, you may not have watched it, but you have watched Forrest Gump. Famous quote, "Stupid is as stupid does." Very famous line, okay? This is the joke on Koto, but Forrest Gump is a rich guy, right? So it's a good wish. So stupid is as stupid does. Koto is stupid, and as stupid does, and maybe they get lucky. And this is also from Forrest Gump, okay? Run, Forrest, run, several times, okay? Because there's a runtime problem in Japan. They don't get enough runtime. So if Koto can only run, maybe they discover something for us. Okay, so I'll stop here. Actually, I have one more slide for the HEP group, but okay, thank you for your attention.